dry fiber materials have been cut into plies of the correct orientation and shape for producing composite propeller blades. Those plies are kitted and then sent up to the layup and preform cell, which we'll walk around now. So now we're looking around the preforming cell where individual dry plies are stacked up and formed to produce a propeller preform. So we start to see a blade taking shape. Here you can see the laser projectors that we have fitted to each of the preforming stations. And you can see the laser pattern being projected down onto the preforming table there. So the preform tool is not located in there, but you can see how the laser patterns are used to locate plies. Now you can see an operator laying up the dry plies into a propeller blade preform. So he's locating them using the laser pattern, which you can just see on the edge of where he's locating the plies there. These plies are all dry, so they have no tack until the binder material is heat activated, which you can see the operator doing now. So he's using an infrared heat gun to activate the binder so that all the plies can be stacked together. Now this looks like quite a simple process, but it's actually very labor intensive and takes a lot of skill and a lot of time to learn. After layup of a blade preform, the preform is transferred to a vacuum bag where vacuum is applied, and the vacuum bag is then placed into an oven to consolidate the preform ready for the next operation. There are 2 preforms per blade, one for each face, and they get combined the next operation to form what begins to look like a propeller blade. And that next operation is foam injection, where we take the 2 preforms, one for each face, put them together into a mold and inject foam into the center. And that foam injection process takes place in an automated foam injection cell. So that consists of 3 central foam injection machines. So they handle all of the chemical mixing and dosing and injection at correct temperatures and flow rates into the mold. And each one of the 3 injection machines is mounted on a sled so that it can be repositioned quickly to service multiple injection stations. And these injection stations consist of a clamshell mold, which is hydraulically controlled to allow it to be opened flat and then closed shut for the injection, and also contains automated heating, cooling, and pressurization equipment. And now you can see into the foam injection cell. So we have one central foam injection machine mounted on a sled. And off to the left and the right, you have multiple foam injection stations, each equipped with a foam injection mold. Here we have a close-up view of one of the foam injection molds. So we're looking at one face here, so both faces are open flat, and into each face we apply one dry carbon fiber preform for each face of the blade. This is a clamshell mold and it's hydraulically actuated, so once the preforms have been placed inside and a special treatment is applied to ensure that the foam bonds well to the composite, the 2 halves of the mold are closed together. This is all automated. So after the operator has inserted the preform, the machine takes care of the rest. The 2 halves of the mold are brought together, and the preform is heated and prepared and pressurized, ready for the foam injection machine here to be brought over and inject a pre-mixed foam mixture into the mold. So you can see here closed molds with the top plugs inserted after injection. So these are now heating and curing the foam with the dry carbon fiber on the outside. So we have the foam core with the dry carbon around the outside, which is now in the shape of an airfoil. Here you can see a close-up of the dosing head. So all the relevant chemicals are injected into, or pressurized and brought into the head, where they're mixed and injected into the tool via the nozzle there. At this point, we now have our 2 dry carbon preforms on each face and a foam core in the center, which now look like a propeller blade and have something approaching airfoil shape. And we then, around the outside of that preform, apply some braid. Braiding is something of a Doughty speciality, and it involves passing the blade preform back and forth through the braider while the braider winds carbon or glass tow around the outside of the preform in a special way that gives it a unique combination of both high speed and precise manufacture, but also excellent mechanical performance. So we have two braiders at Doughty. They're both 192 carrier Herzog braiders with bidirectional linear traverses, so we can braid in both directions. And you can see in the foreground here some of the carbon carriers that we use for braiding. Looking a little bit closer now, you can see the individual strands of carbon or glass coming in from the carriers mounted around the outside of the braid ring. So there's 192 carriers, each fitted with a bobbin, and half rotate in one direction, half rotate in the other direction, and they follow opposite sinusoidal paths, so they braid round one another. And you can see in the center of the image there is some braided material. So that's an offcut from production of a blade. It's black and white because it contains both carbon and glass. And you can see that the sort of unique composite structure that it produces. Here we have a close-up of a mandrel onto which we mount a blade. And here you can see a braider running with half the carriers going one way and half the carriers going the other way. And you can see how that forms this braided material that goes around the outside of a blade preform. You can see one of the operators here who's making a development blade. So this is not as polished as a production process, but all of our production braid at the moment is military, so this is all I can show you at the moment. And you can see here a fully finished braid preform with ply drops trimmed into the preform. The edge of the braid is a little bit ragged here because it is a development product. But you can see we now have our blade preform fully encapsulated with braid material. At this point, the dry carbon fiber preform is almost ready for resin injection to make the final composite blade. We just need to add a few finishing touches and also to attach the metal root fitting onto the blade, which provides the structural retention of the propeller blade when it's rotating to the hub. We call this operation build. Unfortunately, there's very little I can show you because it's very proprietary, the way that we attach the composite blade to the metallic root fitting. But we do have a series of individual stations you can see on screen to which the blade preforms are mounted, and we do the special preparation and attachment of the metallic root fittings prior to resin injection. At that point, the dry composite is completely finished and is ready for resin injection. At this point, we transition across to the resin transfer molding, or RTM cell, where we put our blade preform, which consists of a foam core surrounded by dry carbon and glass materials, into a mold and inject it with resin under temperature and pressure, where the resin is cured and solidified to form the final composite blade. The RTM cell contains a series of bespoke RTM rigs. These rigs are a little bit different to conventional RTM rigs in that they consist of molds which are mounted vertically in presses which operate horizontally. And within the cell we also have capability for automated injection and dispensing and mixing of resins. So now you'll see various views through the RTM hall. So we're looking along the central aisle here with RTM rigs on the left and right. We're now looking at the front face of the RTM rigs. And You can see also some steps going up there on your right. The blades are about 7 feet in length, so the rigs are approximately 2 stories. We're looking from the top level now along the hall, and you can start to see in between some of the open mold faces. So if we hover on one of the presses for a moment, you can see labelled mold face and the injection control unit, and also a root hotbox, which we use to heat the preform prior to putting into a heated tool. On screen, you're about to see old injection control units. These have now been replaced with automated injection control units with digital control and data capture. But unfortunately, we can't show you these because some of the technology involved is proprietary. So now let's look at a mold tool with a blade preform mounted in it. So first of all, we'll look at the inside of the mold half that doesn't have the preform mounted to it. And you can see clearly the outline of the mold cavity. Then we transition across to looking at the other half of the mold with the preform mounted inside it. So you can see it's mounted with the root at the top and the tip at the bottom. And you can clearly see all the dry carbon and glass materials in black and white respectively. I should say that, again, this is a development preform, so it's not quite as tight and neat as our production preforms would normally be. It was in the early stages of development. But it is at least a civil product that I can show you. At this point, we close the press and inject the blade, and what comes out the other end of the process when the part is cured and we've opened the tool is a fully injected composite blade, as you can see mounted in the tool in front of you. All of the glass material at this point becomes transparent, so the blade is almost exclusively black, with a little bit of resin flash around the outside. And you can see here a finished development blade being modelled by a couple of my colleagues here. All that's left now in terms of composite processing is to perform some finishing machining on the blade that involves deflashing and tidying up the root in particular. And that happens in a CNC mill. Now that the composite part of the blade is complete, which includes all the structural elements, the next step in the manufacturing process is non-destructive testing to validate that the blade is defect-free. And that all happens in our NDT suite, where we have A, B, and C scan UT capability, as well as digital X-ray machine, CMMs, and dye penetrant inspection capability. A lot of our blade inspection technology is very proprietary and involves a lot of automation, and we're able to detect extremely fine defects within the composite propeller blade. Sadly, because it's so proprietary, there's actually very little from this suite that we can show you, other than a little quick look at some manual A scan and also a little look at some CMM. And the CMM inspection that you can see here is of a hub for one of our propeller systems. Once NDT have confirmed that the composite blade is defect-free and good to fly, we'll proceed to add all the finishing touches to the composite blade that make a final aircraft propeller blade. The first of which is to add a cuff to the inboard part of the blade, where we define the airfoil in that region. And this has two functions. Firstly, to give an aerodynamic shape inboard, but also to offer some protection to the composite in this structurally important region. We perform this operation in a foam cuff cell by reactive injection molding. Okay, let's take a little look inside the foam cuff cell. So you can see in front of you a high pressure foam injection machine labeled, and also a foam injection mold. We have two of them in the foreground there. The high pressure foam injection equipment mixes, doses and injects all of the foam precursors under very high pressure into the tool. and we mount our blades horizontally inside these tools with the root and the tip hanging out of either end. And just the inboard region where we need to define the airfoil with foam cuff is cuffed, which you can see on screen in yellow in front of you. With the airfoil fully defined, we now apply paint and polyurethane coatings to the blade. We have dedicated paint and polyurethane spraying facilities. We can alternate between automated and manual hand spraying, depending on volume, end use, or the type of coating that we're applying. And all of our coatings are applied in dedicated spray bake booths, so we can spray and cure the relevant coatings all in one facility. Here we have a view into one of our spray bake booths of an operator manually doing the last preparation for manual spraying of a blade and performing the paint spray operation as well. Sadly, I can only show you a manual spraying operation because our automated spraying equipment is currently being recommissioned, but we do have robotic spraying capability. So the blades are very nearly complete now, and it just remains to add erosion protection in the form of a leading edge guard and de-icing capability in the form of an electrothermal de-icer overshoe. Electrothermal de-icer overshoes are manufactured in-house, and our metal leading edge guards are manufactured externally at a supplier and bought in, and then both of those items are applied in a cell within the factory. We're in the overshoe manufacturing cell now, where you can see some overshoe molding mandrels. Overshoes are a combination of a flexible electrothermal de-icer system and a series of different erosion and impact protection materials, all molded together on one of these mandrels to fit onto the leading edge of each different blade type. The overshoes are vacuum bagged and cured in an autoclave, and you can see here a series of vacuum bags ready to go in the autoclave for cure. These are then laid up onto the blade by hand and bonded down with a special process that we use to attach them so that they perform their function during the service life of the blade, but can be easily removed at repair. You can see here a blade leading edge being prepared for bonding of the leading edge guard, which is attached. These are all still manual processes. And then we can see a blade with the overshoe and the leading edge guard fully attached that just needs a little bit of preparation and tidying up prior to being sent off for blade balancing. At this stage, the only remaining operations for completion of the composite propeller blade are to check its balance correctly and to record its natural frequencies. And on screen now, you can see a fully finished blade ready for assembly into a propeller system. Completed blades are then ready for assembly of the propeller system. That involves attachment of the backplate to the hub, as you can see on screen in front of you now. And the blades and bearings are then assembled into each of the blade ports on the hub. And finally, the blade spinner is attached to the front of the assembly, ready for transport to the customer to fit to their engine. And you can see now into the propeller assembly hall, where each one of these white discs shows the area in which one single propeller assembly will be assembled. If they look a little bit empty at the moment, that's because all of the product that we had going through on the days we were filming was military, and we had to get it all out of the way so we could film the area. So unfortunately, you can't see any being assembled live, as it were, but I can show you what an assembled propeller system looks like, both without the spinner, as you can see on screen at the moment, and then also when the spinner has been fitted to the propeller assembly as well. A very big part of what we do at Doughty is repair and overhaul of propeller systems, and it's also one of the big advantages of our new factory, that a lot of the R&O work that was done at a separate site in Gloucester has now been brought into the same factory as all of our OE facilities, so we're able to pool all the expertise in OE blade manufacture and repair and overhaul to offer an even better service to our customers. So for a brief overview of the repair and overhaul process, either at defined intervals or after certain minor damage events, blades or propeller systems will be returned to us by the customer, where they'll be stripped of certain elements that might include leading edge guards or paint and polyurethane coatings or the foam cuff for detailed investigation and NDT to identify any areas of repair that might be required. Those repairs will then be carried out, so that might be composite repairs or paint and polyurethane or foam cuff. And then after the repairs have been completed, the blade will then be refinished with paint and polyurethane coatings to bring it back to its original condition, ready to return to the customer. So what does that look like in practice? Well, you can see here a blade that's come back from the customer with some minor damage identified. Now you can see the blade when it's been stripped back, ready for inspection and NDT. And a blade that's been repaired, so some minor composite repairs and the cuff replacement. And then a fully repaired and finished blade back to its original condition, ready to go back to the customer. All of this work happens in our repair and overhaul workshop, which is co-located with our OE facility. And we have capabilities for remachining of hubs to tidy up any areas of metallic wear. But it's not just at our main facility in Gloucester where we perform repair and overhaul services. We have a network of satellite facilities around the world, and we also have a large mobile team of field service representatives who are able to perform repair and overhaul services for customers at their facilities worldwide. And you can see here a couple of Doughty props that have been dismounted from the engines for one of our field service representatives to work on them. And you can see another prop here, Doughty prop being worked on. So we spent a lot of time talking about our current generation of products, but I'd really like to now focus on the future. So the aerospace industry is changing very rapidly, with sustainability a key concern for passengers and airframers. Fortunately, because of the high efficiency of propeller systems, we're in an excellent position to help deliver the future of sustainable flight, and there are lots of opportunities coming up in the market to do so. So in order to deliver the next generation of world-leading composite propeller systems, we've recently completed a 4-year R&D program, digital propulsion, with the National Composite Centre, the Advanced Manufacturing Research Centre, and the Manufacturing Technology Centre, all funded by the ATI. And this has allowed us to develop state-of-the-art technologies across the propeller system, so across aerodynamics, aeroelastics, composite and mechanical design, manufacturing technologies, new materials and processes, and new control systems, as well as testing. There's far too much for me to touch on here, so I'm just going to focus on a few interesting developments related to materials and process technologies, but it's a really exciting time to be in propellers at the moment. One of the big themes of our R&D work has been automating the manufacture of composite elements of propeller blades and propeller systems. You might have seen from our process that we have elements of the process that are very automated and elements that are still very manual. So a big element of our R&D focus has been to look at ways of putting carbon down precisely, accurately, and at high speed and at low cost. We've been very successful with developments we've had there with the NCC and AMRC. We've also been looking at secondary processes within the composite manufacturing process. So a really successful example you can see here has been automated trimming of elements of preforms. We're really pleased with the results we've had from this. We've also looked at new materials such as thermoplastics in order to explore new methods for producing sustainable propeller systems. And that's been very interesting for us to explore a completely new manufacturing process and material. And we've learned a lot of interesting lessons. We also use a lot of foam and core materials at Doughty, and we've explored methods for automated forming of thermoplastic cores, again for reasons of sustainability and recyclability, but also to be able to produce high precision cores at low cost without recourse to machining. And we've been very successful in a new process that we've developed at Doughty, and have used the AMRC to help mature. In terms of internal development, we have capability for offline process development of all aspects of propeller blade manufacture, all the way from ply kitting up to finishing. And one big area of focus for us in this environment has been RTM mold sensorization for understanding what happens in the tool. You can see in front of you there an RTM tool that's been dismounted and has been drilled and tapped for lots of sensors to be inserted. And we've also looked at developing our own proprietary forming processes to eliminate the need for manual drape when producing composite propeller blades. All I can show you is a slightly ambiguous looking coffin-shaped tool here. All I can say is that we put dry, unformed materials into this very simply, very easily, and that can also be automated. And out the other end comes a perfect, highly complex preform ready to go into a propeller blade. We also have internal capabilities for 3D printing of tools and jigs, as well as sub-elements of development propeller systems. And in the line of more advanced additive manufacture, we've been working with our colleagues within GE Aviation and GE Additive to develop additive manufacturing routes for some of our propeller control system components that would traditionally be machined from forgings. We're now able to produce those additively, and the new designs that leverage this new process are much lower in weight, which is really exciting for future sustainable flight, and have been subjected to all kinds of aggressive tests, such as the fire resistance test you can see on screen, and have passed with flying colours. So we look forward to using them in future applications. Let's pivot now away from composite manufacturing and processing, back towards an overview of some of Doughty's design capabilities. The propeller system involves not just the composite blades, which we've focused on quite a lot today, but also the mechanical rotating assembly that the blades interface with, so the bearings and the hubs, the backplates and the spinners, as well as all of the control system architecture, so the overspeed governors, electrothermal de-icing equipment, and all of the hydraulic control for pitch change and propeller blade angle of attack control. Doughty propellers, we have very advanced analysis and design capability for all of these individual elements, so aerodynamics and aeroelastics and acoustics in the performance team, as well as ice accretion and de-icing. We also have very strong capability for structural analysis in metals and composites, and control system design for electrohydraulic control systems and electrical systems, as well as all the composite design that we've already talked about. As an example of some of our world-leading design and analysis capability, on screen you can see the outcome of a performance study of a propeller system as installed on an aircraft. And it's not just the individual tools and analysis capabilities we have, which are very advanced. Because of recent R&D programs, has been to take all of these very high-level design capabilities in individual areas and to bring them all together to allow multi-objective optimization studies to look at thousands of iterations of designs and the impact on all of these different areas simultaneously in order to produce the best possible propeller system design. And the outputs of those optimization studies are input into our parametric CAD models for propeller system designs. And that's what you've just been seeing on screen. a parametric model updating itself between a 6-blade and a 7-blade system design, and changing all the design definition of all the mechanical system for the propeller. Over the past couple of years, we've also had some big advances in process simulation, an example of which is RTM flow simulation that you can see on the screen in front of you. And we've also been developing composite forming simulation. The advantage of these process simulation techniques is that we can perform concurrent manufacturing process design and part design to really optimize both the structure of the part and the process. Now for the final part of the tour, we'll take you around an area that ordinarily would be completely off limits for anything but a virtual tour. So there are some advantages to this format. And we'll take you around the Doughty propeller test facility. So this facility is really one of the jewels in the Doughty crown. We have a propeller testing facility with proprietary testing rigs for all elements of a propeller system, and we're able to characterize propeller performance under static, fatigue, environmental loads, and all kinds of other complex flight and performance conditions that might be relevant to a propeller system. And on screen we can at least show you a few glimpses of some of our capability. So you can see here a propeller blade being subjected to a particular kind of fatigue testing. We test it under lots of different regimes. We also have a facility for spinning up propellers to understand their loaded performance. You can see here a 3-blade configuration on test, and this is a high-speed camera showing a propeller system rotating at about 1,000 RPM to understand how the blades deflect under different operational conditions. We also have facilities for testing all the metallic hardware. So you can see here a particular kind of fatigue test being applied to a propeller hub loaded under all 6 ports. And we also have some complex hydraulic and electrohydraulic control system test facilities. So hopefully I've given you a good overview of our capabilities and the technologies that we're using here at Doughty, both currently and for the future. And that concludes the tour. So thank you very much for your attention, and we look forward to taking some questions shortly.
Okay, thank you very much. Hopefully all the audio and video worked for everybody. We've got a list of questions through now, so before we run through those questions, I'll just introduce you to the people we got in the room. So we have Datu Kumar, who is the lead composite blade designer for Doughty. We have Jordan White in the room, who is lead ME for the RTM and composite build area. And we've also got Mike Davis in the room, who's been intern with us for the last year from Brunel University, who's been, he's the chap who did all the filming and all the editing and put everything together today. So thanks very much, Mike, it was very good. Of course, I'm James Trevarthen. I'm a senior materials and process engineer focusing on composites here at Doughty. So I've got a series of questions here. Jeff, was there anything you wanted to add before we do the questions?
You're on mute.
You're on mute, Jeff, but I think that's that we're okay to carry on.
Yeah, please do.
Okay, so I've got a question here from Martin Goldthorpe from Torre Advanced Composites. What are Doughty's plans for new processes and materials, and is there a timescale on any plans? Yes, okay, well, I guess I should probably take that, shouldn't I, for materials. We have, in terms of the composite processing, a lot of plans for automating how we produce our composite structures, particularly up to RTM. So we have a few different processes that we've had in development for the last few years. One was a focus on automated forming of existing cloths, and the second focused on direct deposition of carbon. So I can't say exactly how either of those processes work. There are a few sort of Doughty specific slants on them. Both of those at the moment focus on dry fiber material, but we have started to look at just at the simulation stage, process simulation stage at the moment, options for including thermoplastic pre-impregnated materials and also thermoset pre-impregnated materials. One of the reasons we haven't really made a commitment to either of the either dry or pre-impregnated materials or thermosets or thermoplastics is that we're trying at the moment to evaluate all of our new designs for sustainability, both in terms of energy usage and material usage during manufacture, but then also at end of service. And to do that, we have to come up with basically new design methods for assessing sustainability. So everything's still in the mix. We haven't made a decision on anything at the moment, but in terms of timescales, I think we're looking to have made a commitment to one of these streams, probably within the next 6 to 9 months. And then in terms of other processes outside of the composite, then as you've seen in the video, we're looking a lot at additive manufacturing for some of our metallic parts. And we're also looking at new finish line processes to improve automation there. I've got a question here that I'll probably direct to you, Jordan, for manufacturing. So how did Doughty use Industry 4.0 principles for manufacture? And that comes from Joe Summers of Airborne.
Okay, as you can see in James's tour, we've been doing a lot of flow modelling. There's been some thermal and mechanical modelling that we've been doing on tools to make sure that we're getting the right part every single time. We're looking at drape analysis, how we use that to form parts better, reduce defects, and we're collating all that information. We're trying to identify what are the critical processes, what is good data to get, what is going to make an improvement. We don't want to be collecting data on everything because that doesn't always add value. And I guess the hard bit of it is storing that on a data lake because we have to be cyber secure. So it's about having that data, storing it correctly and having useful data, not just all data. So anything else?
No, I think that's a good point. So it's about trying to identify where we can have quality data capture and also process control.
So we've got like a operator system that they enter in data. We record from chart recorders as well. We can use all that data to help solve some of the problems we see.
Yeah, thank you very much. I have a question here from Tim Sell of Composite Innovations, and he asks, are you doing anything new these days compared to the traditional methods which have been very successful at Doughty for decades? So I guess, Jordan, you might like to talk a little bit about how the current process has changed in the last 10 or 15 years, say, and then I can talk a little about what we might do in the future.
Yeah, so I guess I kind of said some of it in the previous answer. So flow modelling, the drape analysis, that's really helped us in identifying our problem areas. And then automated injection machines, having control over the variability, reducing that variability in our parts or our process, so we can identify where the defects are coming from by making step changes. Yeah,
so I suppose the changes in the last 10 or 15 years have been the increase in automation rather necessarily than changing a lot of processes. So the foam process was completely manual before, wasn't it? Whereas now it's entirely automated.
Yeah.
I have a question here from Catherine Jochen from Strathclyde University. So how has automation been incorporated into the development of processes at Doughty? So I guess that probably refers more to what we're doing with automation in the future. I think the answer with that is that in the last 4 years, we've been doing a big government program where we've been updating everything we do at Doughty, including composite processes and manufacturing. How we built automation into this development is to basically bring it right into the beginning of the design. So Doughty's been working with me on some new concept propellers, One where we look at just automating the manufacture of an existing propeller blade design, and one where we completely redesign the propeller blade to be automatable in terms of manufacture. And the benefit of the second approach is more than a doubling of the cost savings, the performance improvements we can achieve, not just in the manufacturing process, but also in improving the design of the part as well, by factoring in consideration of automation, so we don't receive any debits on the material performance or the structure performance because of accommodations we've had to make for manual manufacturing. So I hope that answers that question. I've got another question here from Alex Edge of Procure Materials. What manufacturing technologies are DATI exploring that will enable the next generation of blades and propellers? So specifically, Alex is interested in hydrogen, UAM, and low fuel consumption commercial aviation. Is there much you can say, Datu, on design of new propeller systems for?
That's a good question. Well, to be honest, as James presented in the virtual tour, there are a few thermoplastic, thermoform. You might have seen the anaform shear analysis. So definitely UAM is something which DATI is specifically looking. We are expertise in the high power range, as you might have seen, but we are also exploring into the lower power range. And the methodology or the techniques, this latest flow analysis or the drapability analysis or the tri-X braid, where we are in collaboration with the catapults, AMRC or MTC, is just collaborating more together to bring in that technology to be more competitive in low power range as well. So thermoplastic, thermoform, tri-X braid, which James and our team have been working on.
So I think the answer is that for the low fuel consumption or UAM or hydrogen options that we're looking at the moment, in terms of the manufacturing process, what we need to do is optimize the process for these smaller scale propeller systems. That's not particularly complex, I'd say. Most of the design challenge or the challenge of these systems comes in the control or the aerodynamic design. I can see Ed Jinks, one of our aerodynamicists, or our lead aerodynamicist, is on the line. He's got his hand up, so I imagine he's got something clever he's going to say now. Ed, do you want to say anything?
Thanks for the introduction. Yeah, it's just on the kind of aerodynamic performance point of view, we're really on across all power classes, as Datu mentioned. There's the kind of higher horsepower C130J and Dash 8, and coming lower in the kind of Saab 2000 type range. There are different product technologies that we can focus on, and whether that's absolute efficiency, kind of more efficient flight, or whether that's acoustic levels as well, and noise levels. And we're constantly finding that between the battle of airframers pursuing ultimate efficiency and lower fuel costs, and the certification bodies and individual airports requiring quieter and quieter props, we're continually being pushed. And so across all of the power classes, we're faced with different challenges, and we have to come up with different product features in order to design for that as well.
Thanks, Ed. That was a really good answer. So I guess in summary, there's a lot to consider for these different classes of propeller system, and it's not just across the manufacturing of the composite blades. That's almost the easy bit. I shouldn't have said that. We have a question here from David Pate of Lilium, and he has asked he said he'd be very interested in learning how bonded joints are inspected and control of the leading edge for dimensional conformity is achieved. So we can't say a lot about how our bonded joints are inspected, other than that we recognise, like everybody else does, I guess, that it's a challenge, and special process control, I guess, is key to ensuring the performance of bonded joints. In terms of leading edge or leading edge dimensional conformity, we use an RTM process. So one of the reasons that we use that process is to achieve dimensional control of the airfoil. And then all the elements that build onto the RTM process, we have to, again, be very careful about how we control processes to ensure that we get repeatability of airfoils at leading edges and everywhere else. We use, I guess, typical dimensional inspection to ensure that they remain within control, but the real key there is to use the right processes and control those processes out, get dimensional conformity at the leading edge. And I've got one more question from, let me just find this was a recent one, Richard Newley. Are we pleased with the new facility, and are there any key advantages over the old factory? John, you're probably best placed to answer that, aren't you?
Yeah, very happy with the new facility. Beforehand, after the fire, we were separated across Gloucestershire, and that made it very difficult. Engineering was on one part, commercial were on another, manufacturing was on another. It was very tough, so being under one roof has really helped us. We can get, everyone can go see the parts, so we can quickly diagnose and resolve problems, and we can really come together as a team in the site. Having the option to choose our flow and how we want everything to be placed on our factory is helped our lean progress, so we're really happy with that. We've been able to set up how we want, so yeah, that's been really good.
I think also saying that our response team time to the customer has really increased. As James mentioned, our R&O is also under the same roof, so now they can use some of the techniques with the OE blade, and our turnover time has really increased under one roof, so that's really good.
Brilliant. All right. Well, I think that's a yes. We're happy with the new facility. We're very close on the end of our hour-long slot, so I guess I'll say thank you very much for your time and your attention and all the excellent questions. I think you have our contact details in case you have any more questions, and I'll probably hand over to Jeff to wrap up.
Okay, thanks, James. Gosh, 3 o'clock. I must say, time flies when you're enjoying yourself. I'm sure I do speak on behalf of all the attendees today that was an absolutely fascinating and informative tour, full of information, which we can take our time to absorb. So it was brilliant. Thanks very much indeed for that. Just a quick word that's struck me today and on the preview of the tour I had the other day, and also with the virtual tour we had at AMRC. A virtual tour is not a next best substitute, really, for, in my opinion, for a physical site tour. It's a very viable alternative with certain advantages. You mentioned one, James, that the testing facility, for instance, would be very difficult or impossible to show on a physical site tour because of confidentiality issues, but you could hand-pick things, which gave us a big insight into things. Also, without labouring the point, a virtual tour, you can hear clearly, you can see clearly. Flow charts, in my opinion, really help to understand the complicated nature of your processes there. So anyway, I said at the beginning I'd give you just very brief details of SAMP, because I know a few people attending today are not SAMPy members. And most of the things we offer financial support to students and young working engineers, graduates who are in place in industry. That's one of our main focuses, really. So we offer travel grants, for instance, for students to go to attend conferences to present their work. That helps. We've started to organise some constructive composite competitions where students are asked to sort of design and build a certain structure to perform a certain task. And we have a student seminar once a year and other student competitions. And also a technical seminar, which we run once a year. And incidentally, we had our first virtual technical seminar by default, it might say, in February because of COVID virus. And we felt again that there were some advantages of that. And our next technical seminar in February. It's probably going to be a hybrid event. Anyway, look, if anybody here wants to know more about SAMPI or is keen to join, that would be great. And our website is sampi.org.uk. So in conclusion, thanks for everybody attending today, and particular thanks to the Doughty Propellers team. Thanks to James for a brilliant technical exposition. And the colleague on your right, James, did you see he's done all the filming? His name is, oh, I missed the name.
Michael Davis.
Oh, you're Michael Davis, right. I only know you by email. Well, thanks very much, Michael, for the filming, which was absolutely excellent. And somebody we haven't seen today who took part in registration and screening of participants is Sue Edwards on the IT side, who provided and together with Michael, provided the platform for today. Well, look, I better wrap up. It's been great to see you, in inverted commas, all here today. Hope to see you again in the near future for another of our SAMPI events. And goodbye and take care until next time.
Brilliant.
Okay.
Thank you very much.
Thank you.
All right, cheers.
Bye.
Thanks very much. Great, Joe. Thank you.
You're welcome.